A warm hello to everyone watching this presentation. My name is Vishal Rimal, and in today's presentation I'll be talking about the review on electrochemical kinetics of carbon dots. I belong to the Department of Chemistry, Birla Institute of Technology, Mesra in India. So let us begin. So in this presentation I'll first be going through the introduction on what carbon dots are, the synthesis methods, the electrochemical kinetics of carbon dots, and finally the conclusion. So before we move ahead, I would like to say one of the most famous quotes by Richard Schwartz. So it is said that the impact of nanotechnology is expected to exceed the impact that electronics revolution has had on our lives. So let us begin with the introduction. So one of the most abundant elements, carbon, is found almost everywhere, from sun to the living organisms. We can't even imagine our life without carbon. In the recent years, carbon-based nanomaterials like carbon nanotubes, fullerenes, graphene, and nanodiamonds have attracted a widespread attention. However, the preparation and separation of nanodiamond are difficult. Carbon nanotubes, fullerenes, and graphene have poor water solubility and difficulty in providing strong fluorescence in visible areas, and this greatly limits their applications. So, what should we do in order to counter those limitations? We can use carbon dots. Now, what are carbon dots? Carbon dots are novel carbon-based nanomaterials known for the small size and relatively strong fluorescence characteristics. They are also called carbon quantum dots in many of the manuscripts. Carbon dots are zero-dimensional materials and they have a size well below 10 nanometers. Carbon dots were discovered during the purification of single-walled carbon nanotubes derived from arc discharge suit by gel electrophoresis by Xu et al. In 2004. So this is the reason why they are called carbon dots. This is an image from one of our former manuscripts which was published in Applied Nanoscience, and so they simply appear like dots when seen through TEM analysis. So this incited subsequent studies to exploit the fluorescence properties of carbon dots and to create a new class of viable fluorescent nanomaterials. Carbon dots in the recent years have emerged as an excellent alternative to classical metal-based semiconductor quantum dots, or Q dots. Carbon dots generally possess an sp2 conjugated core and contain suitable oxygen content in the form of multiple oxygen containing species, and they are represented by carboxyl, hydroxyl, and aldehyde groups, and are below 10 nanometers in size, as I've already discussed in the previous slide. It's important to note that the structure of carbon dots has been studied for quite a lot of time. However, we still do not know exactly what goes into and what makes it such a miraculous nanomaterial. So carbon dots have evolved as a favorable choice, most prominently due to advantages of convenient synthesis, prominent biocompatibility, colorful photoluminescence, as well as factors like low cost and toxicity. Carbon dots have now attracted momentous significance due to their excellent chemical and photophysical properties, as well as the varied applications in chemo, biosensors, bioimaging, drug delivery, catalysis, optoelectronic devices, white light emitting diodes, etc. Now let us go into the synthesis methods for the preparation of carbon dots. The preparation methods for fluorescent carbon dots have been improved by employing a wide range of preparation techniques. However, the top-down and bottom-up approaches have been the most widely used method for carbon dot preparation. Let us first see the top-down approach. In the top-down approach, the relatively large materials, including graphene, graphene oxide sheets, carbon nanotubes, carbon fibers, carbon suit graphite, etc., are broken down into small pieces as sp2 fluorescence carbon nanostructures via the methods like laser aberration, arc discharge, and acidic and ultrasonic chemical, hydrothermal, and solvothermal exfoliations. Although the first reported fluorescent carbon materials were prepared by purification of single-walled carbon nanotubes as a derivative from arc discharge soot, there are, however, limited studies about carbon dot preparation by using the arc discharge methods, whereas this is a generally used technique in the preparation of carbon nanotubes. The bottom-up approach, on the other hand, uses carbon dots as bulk materials and are used as precursors to change to particle forms via chemical and physical techniques, including hydrothermal, solvothermal, microwave-assisted, and thermal pyrolysis. Recently, there has been much interest in the development of bottom-up approaches for the preparation of carbon dots due to the precise control of precursor molecules, ease of techniques, low cost and practicality, and convenience of the procedure with generally non-toxic precursors. So you can see in this image here that when we have got small molecules, we use the bottom-up synthesis to make carbon dots. However, if we have the bulk material, we use the top-down synthesis to generate the carbon dots. So basically, we are moving from smaller molecules to carbon dots and bottom synthesis, whereas we are moving from the bulk material to carbon dots using the top-down synthesis. Now let us go to the main topic of this presentation, which is on the electrochemical kinetics of carbon dots. Now you may ask me, what is electrochemical kinetics? So it is the field of electrochemistry that studies the rate of electrochemical processes. And this includes the study of how conditions such as concentration, electrical potential influence the rate of oxidation and reduction reactions that occur at the surface of an electrode, as well as an investigation into the electrochemical reaction mechanisms. So when it comes to the electrochemical kinetics of carbon dots, we're going to see that carbon dots are mostly used as an electrocatalyst. So what is an electrocatalyst now? An electrocatalyst is a catalyst that participates in electrochemical reactions. A variety of nanoparticle materials have been demonstrated to promote various electrochemical reactions. So the carbon-based materials like nanotubes and carbon dots can be used as electrocatalysts. So this is a very important point here. Carbon dots in the recent times have attracted significant interest as electrocatalysts, primarily because they are non-toxic and inexpensive. We can create carbon dots from almost anything that has carbon in it. So carbon dots possess a large surface area with high conductivity and excellent charge transfer capabilities. Carbon dots have essential surface functional groups like OH, NH2, and etc. We can also functionalize carbon dots, which is a very big asset when it comes to their application as electrocatalysts. The doped heteroatom like nitrogen, phosphorus, sulfur, etc. in the carbon dots effectively modulate the electronic properties of carbon atoms via the intramolecular charge transfer. Now, for the green energy production, oxygen reduction reaction and oxygen evolution reaction are extremely important. However, these reactions are slow and an electrocatalyst is necessary to improve the kinetics. Platinum is often considered the best choice in this regard, but cost is a big concern in their application. So when it comes to the applicability of carbon dots, we can use them in oxygen reduction reactions, oxygen evolution reaction, and hydrogen evolution reaction. There are many other forms, but we are just talking about these three in this presentation. So nitrogen doping has been reported to be a powerful way to modify the properties of carbon materials. Nitrogen doping in the previous literatures was shown to significantly affect the properties of carbon dots, including the emergence of size-dependent electrocatalytic activity for the oxygen reduction reaction. The small size and high stability with good electrical conductivity makes carbon dots suitable as electrocatalytic materials for oxygen reduction reaction. We can say that in the coming years, density functional theory calculations and in situ characterization techniques can help deliver notable insights on the intrinsic characteristics affecting the electrocatalytic performance of carbon dots. Now, coming to the conclusion of this presentation, carbon dots are potential candidates for catalytic application due to the small size, good conductivity, large surface area, and facile surface functionality. The emphasis of the review was to enlighten the community on the electrocatalytic applications of carbon dots and encourage manuscripts pertaining to the subject. With adequate research in the field, carbon dots shall be applied in green energy applications very soon. So that's all for this presentation. These were some of the references which were used in making this presentation, and that sums up the presentation for the day. Thank you so much for your patience and your time in watching the entire presentation. Thank you very much.